In this video, we want to look at physics of the planet and satellite. Physics of the planet and satellite. Let's look at the learning outcome. At the end of this class, we'll know Kepler's law of planetary motion, Newton's law of universal gravitation, and we also know what satellite is all about, and expression to calculate the period and velocity of a satellite. So let's start Kepler's law. A scientist called Kepler, after much study, came up with some laws that helps us to better understand the motion of planets and the satellite. And we call that Kepler's laws of planetary motions. There are three of them. Let's look at what each of these laws is all about. Let me use diagram to explain. Kepler's law there are three of the laws. Let's look at the first one. According to the first one, that if you have the sun and a planet, that each planet revolves around the sun in an elliptical orbit. So this is the sun, this is the distance between the planet and the sun, that each planet revolves around on its orbit, and at each point, the sun is at a focus. If the planet is here, the sun is still at a focus. At any point, the sun is still at a focus. So Kepler's first law of planetary motion states that each planet goes around the sun in an elliptical orbit with the sun at a focus of the ellipse. Like I just shown in the diagram here, the planet moves around, and at every point the sun is at a focus. That is Kepler's first law. Let's look at the second one. The second law of Kepler's second law. Let's still use diagram to look at it. Each planet revolves in an elliptical orbit. At a point, the area covered, let's say we have a planet at this point. This is the planet here, moving. At a point, the planet observes slower motion. At another point, it observed faster motion. So here, faster motion, here, slower motion. But from his observation, that whether faster motion, slower motion, the equal area is covered in equal interval of time. That yes, planets move around the sun in an elliptical orbit. At a point, the movement will be faster. At another point, it will be slower. But irrespective of how the motion goes, equal area is covered in equal interval of time. So that is Kepler's second law of planetary motion. Then we have the third one. And according to the third one, that the ratio of the square of the period of two orbit planets about the Sun is equal to the cube of their average distance from the Sun. If you have two planets moving at a period T1, T2, and at a distance R1, R2, according to Kepler's third law, that the ratio of the square of their period is equal to the cube of their distance. So this is Kepler's third law of planetary motion. So these are the three laws given by Kepler's, and with these laws, it helps us to understand the motion of planets, the motion of celestial objects, and even the motion of satellites with these three laws. Let's look at example how we use this third law to calculate the period. Example, we have a question here. Venus is an average distance of 1.08 times 10 raised to power 8 kilometers from the Sun. Given that the period of the Earth is 1 year, estimate the length of Venus' year using the fact that the Earth is 1.49 times 10 raised to power 8 kilometers from the Sun on the average. How do we go about this? To solve this, we need to get the average distance of Venus, let's say it's R1, and it's given by 1.08 times 10 raised to power 8 kilometers. Average distance of Earth, let's call that R2, is equal to 1.49. In this example, these are the given parameters. Average distance of Venus, R1, is given as this. Average distance of the Earth, R2, is given as this. Period of the Earth, T1, 1 year. Period of Venus, we don't know it. So using Kepler's expression for Kepler's third law, we can substitute. And we say T1 square over 1 year square will be equal to 1.08 times 10 raised to power 8, the cube, 1.49 times 10 to power 8, the cube. So if we simplify this, we'll have the period of Venus to be equal to 225 days. Normally in astronomy, one of the units of time is days. So if you have a question of this nature from the Kepler's third law relating to planets, the period and the distance. So in this question, the two planets that we have the Earth, we have the Venus. We know the average distance of the two planets. The period for one of them is given. So we have to find the second period. So we have used the formula, and by substituting and simplifying, the period of Venus is given as 225 days. So we use expression like this. We find, in this case, we find the period. It depends on what you are asked to find. At times, you may be asked to find either the distance of the second planet, but whichever, with this expression, one will be able to find. Given the 3 parameters, we are able to find the 4th one. So that is how we go about using the Kepler's law. The next thing we want to look at is satellite. Satellite. Satellite is a man-made apparatus designed to be placed in orbit around a celestial body, generally to relate information, data, and some other things to the Earth. So, based on this, we say it's a man-made apparatus. So, based on this, we can say a satellite can be a man-made satellite. So, by this, we are looking at types of satellites. Can be a man-made satellite. Then satellite can also be defined as other smaller bodies, such as the moon orbiting a larger one. So based on this, we have the other type of satellite called the natural satellite. So we have 2 types of satellites. The man-made satellite, which is an apparatus designed to be placed in orbit around a celestial body like the planet Earth, and the essence is to relate information, helps in communication, giving us data for weather and other things. Then we also have satellites, which are smaller bodies, such as the moon, orbiting a larger body. The moon is a natural satellite of the Earth. So based on this, we have 2 types of satellite, the man-made or the artificial satellite, and the natural satellite. Then, let's look at classes of orbit that each of these satellites move. The moment satellite is being developed, the man-made one, it is launched into space. So we have different classes of orbit. For Earth orbiting satellite, we have different classes of orbit. We have the low Earth orbit, that is the first one. Low Earth orbit. Which we represent LEO. We have the medium Earth orbit, and we have the last one, the third one, high Earth orbit. High Earth orbit, and the last but not the least, geosynchronous orbit. Geosynchronous Earth orbit. Geosynchronous Earth orbit. So for satellites that are launched in space, fall under any of these. Some satellites, they are launched far up in space, while some, they are close by. So these are the various classes of orbit for Earth orbiting satellite. We have the low Earth orbit, the medium Earth orbit, the high Earth orbit, and the geosynchronous Earth orbit. So these are the classes of orbit for Earth orbiting satellite. The next thing we want to look at is Newton's law of gravitation. And according to Newton's law of gravitation, that the force of attraction between two masses is directly proportional to the product of their masses, m1, m2, and inversely proportional to the square of the distance. So we are looking at satellite, and we can sketch our satellite this way. If we have a satellite of mass moving with velocity v in an elliptical orbit, if we have this to be the Earth, the radius of the Earth, RE, then the distance of the satellite from the Earth, the mass of the Earth, ME. We can apply Newton's law of universal gravitation, that the force of attraction between our satellite of mass m and the mass of the Earth, ME, is inversely proportional to the square of the distance. So we can, this is the distance, so we can express Newton's law of universal gravitation for two masses, the Earth and our satellite revolving around the Earth. But according to Newton's second law, we have that F is equal to ma. I hope you are not looking at the formula on my sheet because it's the same. So this is Newton's second law expressed mathematically as F equal to ma. So let's call this equation 1, this equation 2. If we equate equation 1 and 2, Fg equal to F, we will have that G me over r squared is equal to ma. And our a here is the acceleration due to gravity, which can be expressed in terms of velocity. So with this, if we simplify, we can have that our velocity v will be equal to square root of our gravitational constant, mass of the Earth, and the distance of the satellite. So all we are saying is that for a satellite moving with velocity v on its orbit in a circular path, from Newton's law of universal gravitation, that the force of attraction between two masses m1, m2 is given as the product, the inverse. Our G here is a gravitational constant. So, okay, if we apply that to considering the mass of the Earth and the mass of the satellite, then we can write mathematically Newton's law of universal gravitation to be given by equation 1. Then from Newton's second law, we have that F is equal to ma. So by equating 1 and 2, we have this expression, and our a here is velocity squared over the distance. So if we simplify, we will have that the velocity of a satellite moving in a circular orbit is equal to the square root of the constant mass of the Earth over the distance. Then we want to get the period. We have known the velocity of a satellite moving in a circular orbit. Our velocity is equal to distance over the time. And the distance we are talking about is the circumference of the cycle that the satellite have to cover. Then the period. So from here, we can say that period is equal to 2 pi r over v. Already we have known v to be that. So substituting v into this expression, we have that the period is equal to 2 pi r square root r over g mass of the Earth. Then this can be simplified further, and if we simplify further, we have 2 pi r3 over 2 all over square root of g m e. So we use this expression to calculate the velocity of a satellite moving in a circular orbit, and also the period of the satellite. And what is period? The time taken to complete one oscillation. So in designing of a satellite, the velocity at which the satellite will move needs to be put into consideration, and also the period, the time that the satellite will take to revolve in its orbit. So if we can know the distance of the satellite, we just looked at the various classes of orbit in which Earth orbiting satellite can be placed. So if we know the distance of the satellite from the surface of the Earth, we'll be able to calculate the period. So these two parameters, they are very important as far as the motion, planetary motion of satellite is concerned, the velocity with which the satellite will move, and also the period of the satellite. So these two parameters, they are very, very important. Then also, we want to look at the total mechanical energy. Total mechanical energy of a satellite. And total mechanical energy, E, is equal to kinetic energy plus potential energy. And kinetic energy is half mv squared. The potential energy we are talking about here is the gravitational potential energy. And it is given by this expression. So if we simplify this, substituting, we earlier computed for our velocity. We substitute for velocity and open the bracket here. If we simplify further, we'll have that the total mechanical energy of a satellite moving in orbit is given by equation 4. So we started total mechanical energy, the satellite launched into space, equal to kinetic energy plus potential energy, and kinetic energy is given by this. The potential energy we are talking about is the gravitational potential energy. Our V, the velocity, it has earlier been gotten as our equation 3, so if we substitute here and we simplify, we'll have that the total mechanical energy of the satellite is given by this expression. So let's solve an example where we can use the equation derived example. The question goes, supposing you want to place a 1,000 kilogram weather satellite into a circular orbit 300 kilometers above the Earth's surface. what is the speed that it must travel? Take the radius of the Earth to be 6,380 kilometers. The mass of the Earth, 5.97 times 10 raised to power 22 kilogram, and gravitational constant G as 6.67 times 10 raised to power minus 11 Newton meter square per kilogram square. So that is the question. How do we go about it? Solution. We know the radius of the Earth was given to be 6380 kilogram. The mass of the Earth was given to be 5.97 10 raised to power 22 kilogram. Gravitational constant G was given as 6.67 times 10 raised to power minus 11 Newton meter square per kilogram square. Then the radius of satellite orbit, R will be equal to the radius of the Earth, 6380 kilometer, plus the distance of the satellite from the surface of the Earth. So if you add this, you have 6680 kilometer. But if we see from the gravitational constant, the unit of distance here is in meter, so we need to convert this to meter too. So we'll be having 6.680 times 10 raised to power 6 meter. So with this, using our formula for velocity of the satellite, G me over R. So if we substitute, we will have 6.67 10 raised to power minus 11 times 5.97 times 10 raised to power 22 all over 6.68 times 10 raised to power 6. If we simplify this, we will have the velocity to be 7720 meter per second. So the earlier expression we derived for velocity of a satellite moving in circular orbit, we have used it here. So for this satellite that will be launched at a distance of 300 kilometers, it will be moving with a velocity v of 7,720 meters per second. Thank you very much for your attention. Please subscribe to my channel and like and share this video.